Okay, this is lesson 3.5. We're looking at the four fundamental forces. So basically what this is all about is the basic theoretical cause of all acceleration in the universe. So on a macroscopic level, we see cars sliding on the ground, people pushing doors open, and those things can actually be explained by the four fundamental forces. These are way more theoretical than things like friction and air resistance, but friction and air resistance can actually be explained with these. So the four fundamental forces, the unique thing about them is that they all work at a distance. So they're all like, as Einstein called them, spooky action at a distance. So I'm going to write that in there. They all act at a distance. Whereas something like friction and air resistance, you have to actually make contact with the surface you're sliding on, or in the case of air resistance, you have to actually make contact with the air. So there's four forces. We're going to go from weakest to strongest. The first of these forces is something you're actually familiar with, and that is the gravitational force. Gravitational force is the attractive force between all masses in the universe. Although it is a force that the average person is most familiar with, this is the weakest of all the forces. Only with large objects such as stars and planets can we easily measure the effects of gravity. The most practical approximation for calculating gravitation is actually an equation we've seen before. That is Isaac Newton's universal law of gravitation. Einstein has a theory called the general theory of relativity, and what he does with this is he explains that gravity actually bends space. So when you have a black hole or something like that, really what it does is it takes typical flat space. I don't really know how to draw it in 2D, and it bends it so that it looks something like this. I mean, if you search general theory of relativity, you'll get some crazy pictures, but it bends it so that it looks like when you're going to a black hole, you're kind of rolling down a hill. So it's some beautiful diagrams with his theory. But again, this is the most basic approximation. Einstein's is more exact. Einstein's equations are more exact, but for what we look at, this works. And like I said, it only works for very heavy objects, very high mass objects, although every mass in the universe has gravity. The pen in your hand is pulling on everything else in the room. It just has such little mass that the gravity is not very much. Again, the weakest of all the forces. The second is an equation that we will look at a little bit second semester. But it's pretty important to show now because it shows a symmetry with gravitational force. This is called the electrostatic force. It's the force between positively and or negatively charged particles. Now that's phrased a little strangely, but basically what the electrostatic force says is that opposites attract and similar charges repel. So if you have a positive and a negative charge, the electrostatic force is an attractive force. They will pull toward one another. If you have two positive charges, they will repel one another. They will push away from one another. And if you have two negative charges, it's just like the positives. They will repel one another. So opposites attract. It's a phrase often used in romance, but it's really a physics term. This is slightly stronger than the gravitational force. Actually, it's a lot stronger. The gravitational force is incredibly weak. So this is a lot stronger, but it is still the second weakest of all the forces. The cool thing about this is that it has an equation that looks just like the gravitational force. You know, technically it has a negative sign here. So there it is. Force electrostatic. Electrostatic force is equal to Coulomb's constant times Q1 times Q2 over R squared. Now, we're not going to do calculations with this semester, but it's important to notice what it is. Let's label the pieces. This is electrostatic force. And like all forces, it has a unit of newtons. We'll just go to Q here. Q is the amount of charge in coulombs. I'll just label both of them. So you always have two charges that are attracting or repelling. Otherwise, you don't have any electrostatic force. And this is the amount of each one measured in coulombs. So, yep. And R is the distance between them, just like it is with gravity. Distance from center to center, that's measured in meters. So you'll have a very small number for that. Usually when you're looking at charges, they're things that are really close together. And K is Coulomb's constant. This is just like capital G. It's a scientific notation number. You know, we will write it in here. It's a very, very large number because this is, one can think that it's because it's larger than gravity. I'm actually going to do 8.99. 8.99 times 10 to the 9th. And it has a strange unit. I wouldn't write the unit down. It kind of confuses people. But here it is in case you're curious. 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. So notice it's the same shape as the gravity equation. Electrostatic force is proportional to the amount of charge for each of these, and it's inversely proportional to the square of the distance between them. So basically what that means is more charge means more force, more distance means less force. Something that I always like to point out about gravity is there's no such thing as repulsive gravity because mass is always positive. There are some theoretical discussions about what negative mass means and if it's possible. So in that case, you would have negative gravity. So if you can invent some sort of negative mass, we'll get you a Nobel Prize. Third is in my opinion, the most challenging to understand, but we won't do any calculations with it. It's just sort of a cool concept. So this is we're going to have a diagram, so you'll need like half a page for it. Okay, so the third one, we're getting to this really strong forces now. Although this is a strong force, we call it the weak nuclear force because there's a strong nuclear force too. Okay. This one's weird. It's the force acting on bosons during radioactive decay. You're probably familiar with radioactive decay. Basically, over time, things like, I think it's carbon. Yeah, carbon can turn to nitrogen over time. Carbon-14 turns to nitrogen. We use that for carbon dating. But a boson is something you've probably never seen before. Basically, it's one of the fundamental particles in what scientists call the Standard Model. I think the better way to go about it is talking about quarks. So neutrons and protons in the center of atoms can actually be broken down further into things like called quarks. And there's a huge list of other particles like it, and boson is one of those things. So basically, let's see. So this is stronger than gravitation and stronger than electrostatic force, but this only acts over very short distances. So this is the atomic level. We won't see this beyond the atomic level, and so that's why we won't do any of the math with this. Still a pretty cool concept. Here's what it does. If we have I'll just draw it like this. So I'm not going to draw the proper number of particles here. I'm just going to kind of make it look like a mess of neutrons and protons. Here we have carbon-14. 14C6. So you have carbon-14 sitting here. Basically what happens is one of the neutrons turns into a proton because of something called beta decay. So the electron is expelled. And what we end up with is a totally new particle. So here's what beta decay is. It's when you go from, for example, carbon-14, you go to nitrogen-14. So the total 14 represents the number of neutrons and protons together. So the number of neutrons and protons doesn't change, but since one of those neutrons turns into a proton, 6, your number of protons, turns to 7. Basically, all you need to know is that in beta decay, let's write that. In beta decay, one neutron, it just transforms into a proton, and an electron is expelled from the particle. So the electron is spontaneously just produced inside the nucleus and it's sent out, and you have a neutron that turns into a proton. That's amazing. Super complicated stuff. I believe you'd explain it with quantum mechanics, which is a really advanced type of physics. So how does this happen? Well, it's another complicated thing. Basically what you have is you have something called a neutrino. It's another one of the elementary particles that we don't talk much about in high school physics, but the symbol is like this. It's a little V with an E. That's a neutrino. It passes by an atom, and what it does is it sends something called a W boson over. So here is the weak nuclear force. I know it's W is W boson. I wonder if that's because it's for weak nuclear force, but I'm actually not sure. And as the neutron sends this W boson in, neutrino, as the neutrino sends the W boson in, the neutrino turns into an electron. So I guess it's not entirely spontaneous. So there's the electron being expelled. Here we have a neutron, and it becomes a proton. So what's all this mess about? It's all about, remember what we're talking about, the weak nuclear force. It's the force acting on bosons during radioactive decay. So it's the force right here. It's the force that pulls the W boson into the neutron and turns it into a proton. Really complicated stuff, but amazing, incredibly cool. So that's called the weak nuclear force. It isn't really all that weak. It's quite strong. It just only acts over short distances, and it is much weaker than the Big Kahuna. the strong nuclear force. I think I should write that in there. Let's see if there's anything else. Let me read what I have here. Let's see. When the neutrino loses the W boson, it becomes electron. No, that's pretty much it. Let's write that in. So the weak force, here's what it does. The weak force pulls the W boson from the neutrino and into the neutron. Neutrino's also got a cool history as well. A neutrino was something that physicists, they knew it existed, but they couldn't find it. They couldn't prove that it was there for many years. There's a cool history to that too. We won't go much into it though, unless you're super interested. Maybe we will. And finally, we have the strong nuclear force. This is the strongest of all the forces. Okay, I'm going to read out what I have. It is the attractive force between the protons and neutrons in the nuclei of atoms. It's the attractive force between the protons and neutrons in the nuclei of atoms. So the electrostatic force that we learned on the previous page, it tells us that these protons that are jammed in the nucleus, these protons should be pushing off of each other with a tremendous amount of force. Not only are they all positive, so they're the same charge, so they should repel, they're also very close together. So let's look at a helium nucleus, for example. I've got 2 protons and a neutron here. 2 protons and a neutron. The protons are incredibly close together, so they almost have a distance of 0, so the electrostatic force would tell us something like this. I don't know what number would be on top, but it's almost 0 on bottom, so basically the electrostatic force should be almost infinite, but the strong nuclear force is even more. Let's see what else I have here. At very short distance, oh yes, it only works over very short distances. So 2 protons that are, once they get out of the nucleus, the strong force is actually very small. While it's in the nucleus, the strong force overpowers the electrostatic force and holds the nucleus together. This is considered the strongest of the 4 forces, and it is only strong over short distances, like the weak nuclear forces. So weak nuclear force causes nuclei to change, and the strong nuclear force keeps them together. Not much else to say about this one because it's pretty complicated. From what I read, there's some strange particle that's bouncing between all of these. It just goes from one to the other and bounces back and forward, and it's almost like they're all sticking around for that particle, fighting over it. So yeah, and as they get, it's also pretty odd that as they get farther apart, the strong nuclear force gets stronger up until a certain distance. So as they move apart, the strong nuclear force gets stronger and pulls them back in. But if you can get them far enough out, the electrostatic force will begin to overpower the nuclear force and it'll push them apart. So that's the 4 fundamental forces. What's this all about? Well, these 2 are just cool, and these 2 are forces that we're actually going to talk a lot about. Gravity, it's obvious. We're going to use this one a lot. make sure you have this equation memorized. We're going to use this a bunch. Fg equals mg, where g is positive 9.8. It's positive, as opposed to A, which is sometimes negative. The electrostatic force, although we won't use this equation, it is relevant in the forces that we'll discuss tomorrow, which are called contact forces. Basically, this is the reason why when you push something with your hand, it moves. When you put your hand on a door, and you push the door outward, you're not actually touching the door. What's really happening is on the outer rim of all the atoms in your hand, you have a bunch of electrons that are negatively charged. I should draw them larger. These are negatively charged electrons on your hand. And when you press them up against the door, which also has negatively charged electrons on the outer atoms of the door, you're going to see repulsion. So the negative atoms in your hand, the negative electrons in your hand, are actually just pushing the negative electrons in the door away. Same thing as if you're standing on the ground. When you're standing on the ground, I'll flip it around. When you're standing on the ground has electrons on its surface. Your shoes have electrons on their surface, and so you're not actually touching the ground. The electrostatic force is pushing your feet upward and keeping you from making contact with the ground. So we're going to discuss some force. That force is called normal force. The force of you pushing a door is called applied force. Although we're going to learn these forces tomorrow, it's important to remember that they're actually originated in these four fundamental forces. Pretty heady material today. Just make sure you have it all written down. No calculations for it. We'll do some maths tomorrow. Thanks for your patience. Thanks for watching, and I'll talk to you all soon.